So now we're going to have the first of two talks on automotive safety applications. I mentioned this morning in my presentation, I think automotive safety is arguably the most important sort of emerging application that is rapidly moving to high volume. We're already seeing all of the luxury automakers shipping sophisticated vision-based safety features in their cars, and I think we can expect that to rapidly proliferate down to mid-range and eventually even inexpensive cars, much as has been the case with other safety features, airbags, stability control, and so on. And we're very fortunate to have Paul Zoratti from Xilinx here for the next presentation, because Paul has really deep experience in automotive applications, including automotive vision applications, and he's going to talk about vision-based automotive safety applications. Paul?
Thank you. Good afternoon, everybody. It's 4:30. Everybody hanging in there? It's kind of what I thought. How many automotive engineers? It's funny, when I say that in Detroit, all the hands go up. Jeff made a comment in his opening remarks, and he made it again now, about how fast things are moving in automotive in terms of the deployment of these safety systems. And I had this flashback to about 20 years ago when a young engineer at the time, working with an automotive company and tasked with shaving 5 milliseconds off of an airbag deployment time, took a 94 gigahertz radar sensor that was designed to go into a missile head, strapped it onto a lab cart, took it out into the parking lot, pointed it at the cars, and said, yeah, we can do this. So that was 20 years ago. But it is fascinating today to see, even on TV, right, all the commercials of all of this stuff now truly being deployed out into the marketplace, and it's being driven more and more. So how many people know that if you buy a car in North America, it's in 2015 or 2016, you will have a camera on that car? That's going to be mandated. So when we look at the professionals doing image processing and knowing that we're going to have cameras on every single car, what a great opportunity for OEMs and for inventors to differentiate themselves and get their products out into the market. So what I wanted to talk about today was a little bit about some of the challenges that are facing people that are developing these driver assistance systems, and then use a project that we recently conducted with some of our partners in terms of implementing some of these systems on a device to address those challenges. So to begin with, just to get everybody kind of grounded, when we talk about driver assistance systems or advanced driver assistance systems, what we're really talking about is utilizing advanced sensing technologies, be it radar or ultrasonics or vision, and processing that data to make drivers better drivers. And the way we do that is through a couple of different methods. Number one is making them more aware of their surroundings. So all of these dark boxes in the bottom here are actually features that people would be willing to buy. And so you've got a set of features here that make drivers more aware of what's going on around them. You've got features that will actually issue a warning to the driver if it detects a dangerous situation. You've got features that will take temporary control of the vehicle, and we have those out there already today. Adaptive cruise control, which longitudinally controls the speed of your car to maintain a headway to the vehicle in front of you. So those can be convenience-oriented in terms of adaptive cruise control, or they can be safety-oriented. Mercedes has launched their CitySafe product, which does automatic braking when it detects pedestrians or objects in front of you. The other thing about these systems is once we characterize the environment around the car, we can use that information for performance enhancement, such as side impact detection, where saving a few milliseconds on your airbag deployment time can actually be very critical. The problem that we've had in the past, and that young engineer, that product never got to market, was because no consumer is willing to pay $200 to $300 to $500 to shave my 5 milliseconds off their airbag deployment, because they don't know what that means. But if we can give them an icon in their side view mirror that indicates to them whenever there's a vehicle driving in their blind spot, and every morning on the way to work they see that working, they realize, oh, I can spend $200 to $400 for that. I can do that to make my wife safer. Now we've got the sensors on the car, and we can begin to look at how they can enhance other systems on the vehicle. So we're seeing the early deployments today, and really where everything is headed is this node or this thought of putting multiple features together. So here what I've done is I've picked out 5 different features on the car that people would be willing to pay for. So we start off with a park assistant or a surround view system. And we have a demonstration of this in the demo hall if you haven't seen it yet, but it's basically putting 4, 5, or 6 cameras on the vehicle, taking the input from all of those imagers, stitching them together, and giving the driver a view of what's going on around their car. So we can give them a standard bird's eye view, we can give them more of a 3D view. Another feature is what we're all going to be seeing soon, which is the rear camera, the rear camera on the car. And then we can enhance that with things like picture-in-picture processing to do features like rear cross traffic. So if you've ever been in that situation where you need to back out of a parking spot, but you've got a huge SUV on one side of you, so you back out real slow and you hope you don't hear somebody's horn. The rear view camera actually, if you have a wide enough field of view lens, is able to see down those lanes. So what we can demonstrate is the ability to show the driver the oncoming traffic so that they can see what's coming and stop themselves from backing out. We've got pedestrian detection, again, identifying pedestrians in the vicinity of the vehicle, warning the driver if they're too close. Blind spot detection, indicating to the driver with an icon in the side view mirror when there's a vehicle next to them. And lane departure warning, notifying the driver when they may be inadvertently departing the lane. So here we've got 5 features that an OEM may want to bundle into a system, and they of course want to use one common set of sensors to drive the cost down in order to provide all of those features. So from a developer's standpoint, we get this platform challenge where we need to combine the processing, which can be very different for all of those features, into a single platform. So we've got to worry about having an efficient processing platform because we're talking about a lot of operations to realize those features. It needs to be flexible because of course the OEM is going to say, well, for model A, I want features 1, 2, 3, 4, and 5, and for model B, I want features 2 and 4, plus something different. Maybe I want traffic sign recognition. So we need a platform that we can reprogram basically to fit the needs of all of these different features. And then it needs to be scalable. Jeff mentioned about some of the luxury cars today having many advanced features on them. But some of the lower end vehicles will have maybe only 1 or 2 of those features on them. We need to be able to scale the bill of materials based on the number of features and the type of processing that we're doing. So we really call that the platform challenge. Another challenge is the partitioning challenge. So let's take lane departure warning as an example. I've got a raw input image coming in where my job is to detect the lane markings. So I need to capture the image, smooth it, do some edge detection, some thinning, and then do a lane marking pattern search so that I can identify what I think are the viable candidates for the lane markers. So now I've taken that maybe grayscale, maybe RGB image, and I've reduced it down to an element level where now I need to fit it to a road model, and I probably need to do some lane tracking. And then on the backside, I need to determine where my vehicle is within that lane and figure out when is it right to give a warning to the driver. So the point being here is that these driver assistance processing needs span the whole continuum from things that are computationally intensive and kind of lend themselves to parallel processing hardware to these decision and control processes which really belong in a CPU. And then I also need to worry about vehicle and sensor connectivity as another critical aspect. So we really call this the partitioning challenge because I need to share this data across serial decision-making CPUs and then the computational power of the parallel hardware. So from an architecture challenge, what we're talking about, again, we need the performance for the multiple features that I've mentioned. We need to be flexible enough to do feature bundling variations. We need to be flexible with the algorithms. Designing for automotive, especially when you're doing remote sensing, is very difficult because it's basically an analog world out there. And imagine any driving condition, any geographic location, and you need to be able to handle all of those situations. So as we deploy these systems, we learn more and more about the algorithms and the changes that we need to make for a more robust system. We need to worry about system power limitations and, as always, system cost targets. So what I've shown here is kind of a traditional architecture that kind of approaches, or at least tries to address, the partitioning challenge, in that I've got some, in the front there, I've got an FPGA that's doing some of the heavy lifting in terms of the parallel processing through hardware. I've got a DSP that does the element level processing, and then I've got a microcontroller that kind of handles that back-end decision-making and interface out to the vehicle. So I've got 3 different devices across which I need to disperse all of the processing for all 4 or 5 of the features that I want to implement. So it can become a very complex situation in terms of development, especially when I need to make a change. So if we look at some of the approaches to address those architecture challenges, of course, parallel hardware acceleration helps in terms of performance. Having programmable hardware as well as programmable software is huge because it gives us that feature bundling variation as well as the algorithmic flexibility, provided we have enough bandwidth available between our hardware and software elements. We want to eliminate chip-to-chip interfaces, which helps with our system power issues. And we want to integrate everything into a single scalable device. So that's kind of the ideal world. So you guys have already seen, if you were here for Ben's recent talk, and Jose gave a talk earlier today, and some other people have talked about the Zinc SoC. So what we've done was this project to try to illustrate how these challenges can be met by using such a device. And what's really shown here is that all the features can be thought of as software features with hardware acceleration out in the FPGA fabric. So let's get into the project a little bit, kind of the fun part here. What we did was we took a ZC702 development board, commercial off-the-shelf board. We designed an interface daughter card to that to allow us to take in 4 megapixel imagers. They're 1280 by 800 resolution, running at 30 frames per second. There's an LVDS link from each of those cameras down to the central board. And we implemented our 3D surround view and simultaneously pedestrian detection. Now, the way to think of these SoC type products on the left there is as a data flow model. What you have to remember is that this term all programmability is I can program my CPU, but I can also program and reprogram my hardware. So on the left side is a data flow model, where you may have on the bottom there down in the fabric, this is typically what you would think of in terms of video processing. I've got video coming into my device. I'm going to manipulate it. I'm either going to correct it, or I'm going to distortion correct it, or I'm going to add some overlay, and then I'm going to send it on to a display. So the crux of the algorithm is being done down in the fabric. Now, what's being done by the PS or the ARM controllers in the Zinc device is kind of selecting the display modes that I want to use, maybe providing information that gets overlaid on that video, but very little loading in the PS, most of the heavy lifting being done down in the fabric. The other model to think about these devices as is just purely a software CPU, where I'm going to run my software up in the PS, and then I'm going to identify where are my bottlenecks, where am I spending all of my MIPS, and then create an acceleration block for that. So when I talk to the automotive software guys, they really like that model because it resonates with them. That's typically what you would do if you were doing some form of analytics. So we'll come back to this in a minute. Now, in implementing this project, we actually had 3 partners. They were led by our partner Xylon, but they each were going to contribute a component to the development of this system. In many ways, automotive developers, they have different teams working on different parts of their algorithm, so it's a good way to think about it. The first thing we did was we had our partner Xilinx put together this processing framework. So in the lower left-hand corner, we interfaced to the 4 cameras. We took that data in and we wrote it out to DDR3 memory. So we buffered all of the frames. That way we could make the raw images available to all of the other partners to work on. The other thing in the upper right corner here was we needed a way to display the data. So we put a compact video controller there, multi-layer, which would then go in and grab certain locations in the memory, overlay those images on one another, and we could connect up a display through the HDMI port, okay? So that was the framework. So think about being a developer, being given this framework. I know where my images are in memory. There's an interrupt generated to tell me next frame is ready. I know where to write images that I want output that the compact video controller is going to go grab. So the next phase of the project was to take that framework and add those 2 features that we're talking about. So here you can see the 3D surround view block, which basically goes out, grabs each of those 4 images, the raw images. Those are 180-degree field of view lens on those cameras. So the first thing it does is it distortion corrects those. Then it does a perspective projection to make them look like they're looking top down. It writes them out to memory in the proper location such that when the video controller goes and grabs each frame, it overlays them and we get that bird's eye view. So that's kind of a video processing data flow model. On the right here is the pedestrian detection and ranging accelerator, and I'll get to that in a second. But you can see how the framework was used as the basis for implementing these 2 features. With respect to the surround view, right, we've got, like I was saying, the distortion correction and perspective projection on the top, and we're applying that to 4 images and writing them out so that they get stitched together. And you can see on the right here, those are examples from an actual car out on the road. Those are real, true images. Again, you can see the demo in the demo room. In addition to just generating this top view, again, because we can have parallel paths down in the hardware, we can generate other images, what we call hybrid image. So on the left, you've got the bird's eye view, and to the right of that is just the rear view camera rectified. A lot of drivers like to see that, and actually the NHTSA ruling that's going to force all these cameras to be on the cars is going to necessitate that the driver have that image visible when the vehicle is in reverse. And then I already showed you about how we can do picture-in-picture and overlay those into the rear view camera such that you can do this rear cross traffic feature. So a lot of flexibility just in terms of having this hardware core, this thing called LogiView that allows us to manipulate the pixels and generate different images. Now, pedestrian detection and classification. It's a totally different ballgame. Now I've gone away from video processing to image analytics. What we do is we go out and we grab that image from the rear view camera and we do an HOG SVM approach, which I've heard a number of people talk about today. So we take a detection window and we scan that window across the frame, stepping it through. And at each position, we do the RGB gradients of that window. And what it does, it creates a descriptor for whatever exists inside that window. We feed that descriptor to an SVM module that's been trained on what a human looks like, and it does the detection. Because the detection window is a fixed size, what we do is we put a scaler in front of the HOG SVM so that we could detect pedestrians at different ranges. And I just thought it would be a little bit interesting here to talk a little bit about, well, how much processing power does that take? If we just look at some of the resources that are utilized inside the device, we have 35 DSP blocks running at 200 megahertz each for an equivalent processing power of 6.4 gigamax per second. Another way to think about the processing power is just to add up all of the raw operations that we're doing, the adding, subtracting, comparing. If you add all of those up, it comes out to 30 gigaops per second to support this megapixel image at 30 frames per second. So quite a bit of processing power. And then in the lower left corner there, it's actually an example. I've got a video of that in the demo room where the car's actually moving, detecting multiple objects. Before I talk about the top block there, because I just talked about 30 gig operations per second, 6.4 gigamax per second, I wanted to show a little bit about how much resources are we utilizing inside the device. So now we're talking about this hardware accelerator in the fabric. And so we talk about slice registers or flip-flops and lookup tables, some of the main processing elements inside of an FPGA. And we look at this Zinc device, the 7020, and looking at what's available on that device, and this is an automotive grade device. We're using less than 20% in terms of the computational power of that device to do the HOG SVM, including the scaler in front of it. Now, in terms of memory, we're using a little bit more. It's around 30%, but that can definitely be optimized. Okay? Now, to go up to that top block, I wanted to talk a little bit about the partitioning. So, everything in yellow there is a hardware accelerator. Well, what are the ARM CPUs doing? Well, what they're getting is for each window position and each scale, they're getting what is a candidate window where a pedestrian may be located, and they're getting a confidence value. So up in the ARM CPU, it's sorting through all of this so we don't do multiple counts. So it's kind of aggregating together all of the detections and determining which is the strongest detection. It's doing some filtering. I also wanted to highlight, when you look at the performance of this system, this is just a snapshot by snapshot evaluation of where we think pedestrians are. We're in the process now of adding a tracking algorithm there, which will make it much more robust, because now you know where to look in the image where you had a detection earlier. And then we'll feed that data back to the accelerator block to make it smarter. That's coming in the future. The other thing the PS does is the range estimation and the graphical overlay. So you can see what we've done is we've offloaded all of the highly computational aspects down into the fabric, and we kept all of the kind of the serial decision processing, things that run good on the CPUs up in the ARM processors. This is a picture of the output of the demo. So you can see, what's important here is to look at, and I've got, both systems running simultaneously. I'm doing surround view, plus I'm generating the rear view image, plus I'm doing the pedestrian detection and the overlay. So this is back to that block diagram. Let me see if my pointer has revived itself. So if we think back now to those couple of models that I talked about, the data flow model. So think of the video processing, think of the surround view system where the data comes in, it goes out to memory, it's pulled out of memory into the surround view processor, written back into memory, and then pulled out by the video controller. Very little interaction with the CPUs, other than, like I said, maybe to control the mode and to generate some of the overlays. In contrast, we've got the accelerator here for pedestrian detection, which is going out and, again, grabbing the image from the rear view camera, but now beginning to interact with the CPU to figure out where the pedestrians are. So more of the acceleration model that we talked about. Now, one of the powers just in general of FPGA and of programmable hardware is surround view and pedestrian detection is great when you're going slow, but if you're living in Germany and you're driving down the Autobahn, it doesn't do you much good at that point. However, we've still got all 4 cameras on the car, and we still have access to all of those images. So one of the things that we can do is reprogram the hardware. We can take out the surround view block, and we can put in our optical flow block and do blind spot detection. Similarly, we could take out the pedestrian detection block, and we can put in our rear-looking lane departure warning. This can also be demonstrated on the vehicle in the demo room. We put it in a different mode, and it's actually using the same cameras and doing this type of processing. So again, it's really looking at the state of the vehicle. So we call this kind of our low-speed configuration. I should probably call it low-velocity configuration, high-velocity configuration. Notice, the framework stays exactly the same. It's just a matter of how do you want to process that data. So in summary, what we've developed with our partners, what our role here is to prove out how you could address some of these challenges for driver assistance systems developers. And we've got this driver assistance kit, which is again based on the ZC702 board, and it comes with those two configurations as reference designs. The cores themselves are evaluation cores. They're encrypted, but you do have access to the high-level software to turn the function of those cores into whatever application you want from a software perspective. You can also go in and rip those cores out and put your own processing core in there within that framework. So the reference designs that we give you are actually able to implement all of those features. For further information, of course, the Embedded Vision Alliance site, the Xilinx homepage if you're interested about our products, and that kit that I'm talking to you about can be found at that link. Thank you.
Thank you very much, Paul. Really amazing stuff you guys are doing, and you know, to think that there are over 1 million people a year killed in automobile accidents, even a 10%, taking 10% out of that's, you know, pretty amazing. Hopefully we can do a lot more than that.
For
We
sure.
have time for questions. Questions for Paul? Please raise your hand and we'll bring you the microphone.
Henrik Schubert, Missing Link Electronics. One of the early applications of programmable gate arrays was reconfigurability at runtime. I mean, like the military guys used it. Are you suggesting doing the same thing here, where the moment I enter the Autobahn, I swap out my pedestrian detection because I probably won't need it there, and instead of have a blind view detection?
Mm-hmm. So yeah, that is exactly what we're saying. The implementation that we have today in the Zinc processor, you're able to keep the processor system itself up and totally reprogram the fabric. And that's the way we're doing it today. However, through partial reconfiguration, you can just do individual blocks very quickly. And you know, in talking with some of the OEMs, they're very interested in doing that depending not necessarily the feature that they're implementing, but the environment that they're in. They suddenly drive into a tunnel. They need a different processing block, maybe that's doing some high dynamic range processing that they want to swap in. So the other thing that we're very involved with is ASIL. So it's Automotive Safety Integrity Level. So putting enough hooks into our devices so that you can meet these different safety integrity levels that are going to be demanded by the industry. And that includes doing all of the checking to make sure that when you do partial reconfiguration, you've actually reprogrammed to the right area what you thought you did.
Any other questions for Paul? Well, Paul, thank you very much for the excellent presentation. Really, one of the things that really struck me about your presentation was I've rarely seen a case so compelling for if you give us more processing power, we can turn it into, you know, real value, right? You can provide more of these functions simultaneously. You can do a more exhaustive search for pedestrians. You can use a more sophisticated, you know, pattern matching algorithm. It's great, right? So the more processing power we can get within reasonable cost and power, you know, envelope, the better these products are going to get, and that's really promising for the future, I think. Thank you very much.
So it also lends itself to the smarts of the algorithms and the efficiency of the algorithms.
Yeah.
So all the inventors.
Thank you very much for the fantastic presentation.